Hey guys, in this video we'll be doing some examples on weight and conversion from mass to weight. So let's start with our examples. Now I have some questions here with me. I'll just read it out to you. Okay, so the question says, what does an astronaut of mass 100 kilogram weigh? So there's an astronaut. Let's say this is the guy. This is the astronaut, and the astronaut. This is the astronaut, some disfigured guy here, and he has a mass of 100 kilograms. So the first question says, how much does he weigh on Earth, where the gravitational field strength or the gravitational acceleration is 9.81 meters per second square, or in some cases, as I've told you, it can also be taken as 10 meters per second square. So how much does he weigh? So for gravity, we know a simple formula for gravitational force, which is W is equals to M times G. Weight is equals to mass times gravitational acceleration. So we want to find out the weight. So W is equals to mass is 100, and the gravitational acceleration on Earth, this is the gravitational acceleration of Earth, is 9.81 meters per second square. So this becomes, the weight of this astronaut becomes 981 newtons on Earth. Now let's see the second part of this question. The second part of this question says, what does an astronaut of mass 100 kilogram weigh on the moon, where the gravitational field strength is 1.6 meters per second, or newtons per kilogram, or the acceleration is 1.6 meters per second square. So now they're talking about moon, where the gravitational field strength of moon is 1.6 meters per second square. Now they ask me, what does an astronaut weigh on moon if he would to stand on a weighing balance? What would the weighing balance show? So if it's talking about the weight, so the weight of the astronaut would be mass times gravitational acceleration. Here the gravitational acceleration on moon is 1.6, so the mass is what is the mass? 100 times 1.6. So the weight on moon of the same astronaut is 160 newtons. So if he was to stand on a weighing balance which was calibrated in newtons, this is what the weighing balance would show on moon, 160 newtons, and on Earth it would show 981 newtons. This doesn't mean that your weighing balance is faulty, it only means that the gravitational acceleration is changing. However, the mass of the astronaut on moon, mass on moon would still be 100 kilograms. Mass is an unchangeable property, and this does not change no matter where you are. The mass will be 100 kilograms. So that was our first example, and this was an easy one. Let's talk about some balanced forces and weight. We know that weight always acts on the downward direction. This is the weight. What happens when there is a force that is trying to balance this weight? And for it to balance, it will have to be in the opposite direction. Let's say this is some force. What happens in those cases? Now we'll see. Let's see the example here. A rocket has a mass of 500 kilograms. So this is our rocket, and this is our rocket. These are some flames here. So this is the rocket with a mass of 500 kilograms. The mass of this rocket is 500 kilograms. So the first part says what is its weight on Earth, where the acceleration is 10 meters per second square. So what is its weight? The only formula to calculate weight is W is equals to mg. W is equals to mass, which is 500, times 10. So the weight on Earth is 5,000 newtons. So if this is the rocket, there would be a 5,000 Newton force acting downwards, which is the weight, and we will show it like this. This is the weight, and it will always be acting downwards. Weight always acts downwards. Now they say at liftoff, part B tells us that at liftoff, where it's just taking off, the rocket engine exerts an upward force of 25,000 newtons. So the rocket engine is exerting an upward force of 25,000 newtons to take off. So the question says, what is the resultant force on the rocket? So let's see, let's just change this. Here, this is our rocket again. Okay. This is our rocket again here. And we have found out the weight of this rocket, which is obviously a force, so it acts downwards. This is the weight, which is 5,000 newtons. And in this question, it says if it has a liftoff or an applied force, because obviously it would be applying some force. So what is the resultant force on the rocket? The applied force is 25,000 newtons, and it would be upwards. Because the question says so, and also because we know it has to move upwards, so it has to apply a force upwards. So for the resultant force, we know that this is our axis. Let's take this one as positive, the one on the top going upwards, and the one going downwards would be negative. So the resultant force is simply the sum of the two forces. So let's just take the sum of the two forces. This one would be positive since it's pointing upwards. So this would be 25,000 with a plus sign, plus, since it's a sum, minus 5,000 since this force is acting downwards. So I think we know now how to calculate the resultant. 25,000, and this would eventually become 25,000 minus 5,000, and this would be 20,000 Newton. It would be, because of these two forces, it would be as if only one force is being applied, which is a force of, which is the resultant force. The sum of the two forces would be 20,000 newtons, and this would be applied on the rocket, as in the total force that would be applied on the rocket. Now the next part says what is its initial acceleration. So for the initial acceleration, we have the formula which says Fr, which is, or the F net is equals to m times a. F net is equals to, we know F net is equals to 20,000 newtons, and m, the mass of the rocket, was 500 kilograms. Now remember, this is not the weight, this is the mass. Initially the mass of the rocket was 500 kilograms. We need to find the acceleration. So it's very simple. 20,000 is equals to 500 times a. A is equals to 20,000 divided by 500. This would give me 40 meters per second square. So initially, let's say if so initially it was accelerating, obviously, and you should always remember that the acceleration is always in the direction of the resultant force. So whenever you are confused, just look at your resultant force, and the acceleration will always be in the direction of the resultant force. So the acceleration of 40 meters per second square would be in this direction of the rocket. So I hope you understood these examples, and always remember that the mass is constant no matter what the environment or what the situation is. However, the weight will depend on the gravitational acceleration. So I'll meet you in the next lecture. Thanks for watching.